In this video, we're going to talk about lung ventilation and the role of the pleural membranes and the respiratory muscles in that process. We'll talk a little bit about breathing at rest, which is called eupnea, and then forced breathing, which is called hyperpnea. And then finally, probably say a little bit about atelectasis and how it links to Boyle's law. Mentioned atelectasis, I think, in a previous video as well. This is going back a slide, and the reason to do that is really to point out the role of the pleural membranes, right? Remember, the pleural membranes would be the membranes that line the pleural cavities, right? And it's that dual layered, right? Here's the label. Dual layered serous membrane. The innermost layer, labeled this last time, right? Shrink wrapped onto the surface of the lung is the visceral layer. And then there's a layer on the outside, shrink wrapped onto the surface of the pleural cavity, which would be the inside of the rib cage and the top of the diaphragm. And that's lined by the parietal pleura. And of course, it's really important to keep in mind that there's a fluid layer of pleural fluid between these two. And I think I pointed out previously that that's absolutely critical to maintaining the surface tension between those two, between the outer layer of the lung and the inside of the pleural cavity, right? And the rationale for this is that there are no muscles in the lungs to help them ventilate, to help them fill and expel air. And so it's entirely a indirect process. Ventilation of lungs is entirely an indirect process. All of the energy goes into changing the thoracic volume and therefore the pleural cavity volumes, not into changing the lung volumes directly. Now we will find that one tracks the other for a couple of reasons. Again, I think being redundant here, but because the surface tension between these two layers, right? The surface tension created by that pleural fluid between the visceral and parietal layers, as well as this negative pressure in that intrapleural space. And that negative pressure, so like a vacuum, right? So it's sort of, the lung is sort of sucked up against the wall there because of that negative pressure. And that negative pressure is actually generated, it's kind of odd, but it's kind of generated by the fact that these two surfaces are actually pulling away from one another, which would tend to make you think, okay, well then they're gonna like pull apart, right? Well, the more they pull apart, the more you create a negative pressure between them and the more they're held together, right? So yes, the pulling apart does tend to make them pull apart, but because they're pulling apart, you generate a negative pressure that tends to keep them from actually becoming disassociated. Okay, and that negative pressure here is just a couple of millimeters of mercury on the negative side relative to atmospheric pressure. And we'll come back to that in just a minute with Boyle's law. Okay, so Boyle's law, my pen again. Right? Boyle's law is really simplistic. It's the easiest of the gas laws here. Boyle's law basically says that pressure equals 1 over volume. In other words, pressure and volume are inversely proportional. Or you could also say that P times V equals a constant. And so if the pressure were to go up, that means the volume would have to go down to have the answer stay the same here, and vice versa. Okay? Now, remember, we are changing the volume of the thoracic cavity, not of the lungs directly. And so we're going to have to talk about the muscles that change thoracic volume. And I'm going to do that in a separate picture, but we do have one of those muscles shown, diagrammed into this picture, which is the diaphragm. Right? There are a variety of others, and let's get to the specifics of the muscles involved in both inspiration and expiration in just a second. But for the moment, we're going to say that those muscles are aiding an expansion of the thoracic volume and then a contraction of it, right? And when they expand, right? So think of if the thoracic volume goes up, then because the lung volume tracks thoracic volume, right, for the reasons we just mentioned, then lung volume will rise. And so as lung volume rises, right, and so look at this equation right here. So if volume goes up, what's pressure going to do? It's going to go down. So this P alveolus, that's the intrapulmonary pressure, falls when we inspire, right? And it falls because the volume is going up, right? And so this is our inspiratory phase of the cycle here, right? And so if we look at the pressures relative to atmospheric, and actually we can track the volume of our breath down here, right? Volume's going up. When we expire, then volume will be falling, obviously, right? And if we look at the intrapulmonary pressure, let's follow this one first, it's going to become negative relative to atmospheric pressure. So atmospheric pressure, let's label it out here, right? Air moves in, and it's moving in from this space out here, so PATM. And if you were at sea level, it would be about 760 millimeters of mercury, right? So, and that's fairly constant, right? That's not changing unless, there's a hurricane coming. And as you inspire it, as you increase the volume of this pleural cavity and therefore the lung itself, this alveolar pressure will fall. And so in this phase, the alveolar pressure is going to equal about 759 millimeters of mercury. In other words, it's going to fall slightly below atmospheric, right? That's this fall that we see right here, down to, again, about -1 relative to atmospheric, right? 760 minus 759. So we have about a 1 millimeter of mercury pressure gradient driving, really small, right? Driving airflow into the lungs during inspiration at rest. Okay. Now you'll notice as you pull the thoracic wall away from the lungs, right? You're pulling outward. Guess what happens to that intrapleural pressure? Right? You're pulling outwards, so that pressure is actually going to fall even more negative. Notice already negative over here to start. It's going to fall even to a greater degree. And so even as you're pulling away, pulling the thoracic wall away from the lung harder and harder, the lung will be attracted more and more to that same surface because the intrapleural pressure falls. So it actually helps us keep the lung tracking thoracic volume, and that we don't get a separation there of the two, even though it's pulling harder away from the lung surface, right? That this is a countermeasure in that the intrapleural pressure falls correspondingly and logically to help keep the lung attached to the thoracic wall. Now, during expiration, right, what we're going to do is still 760 out here, right? The weather's not changing. Right? You're still 760 out here, but now what are we doing? Now we are shrinking the thoracic volume, therefore we're shrinking the lung volume, and so our P alveolar pressure is going to rise. Again, go over here, right? If our volume is going down, again, we have a constant as the answer here. If our volume is going down, then our pressure must be going up, and let's make it 761, right? And here's our jump up, about a millimeter of mercury. And now we have a 1 millimeter mercury gradient favoring expulsion of air from the lungs, right, through an open glottis. And here we have our volume of our breath that we took in, right, being expelled in exhalation, right? And so there's Boyle's law and how it helps explain overall lung ventilation. Okay. Now, to jump into this idea of atelectasis, right? If we break this surface tension, right, between here and here, if we were to upset that connection between the visceral and parietal layers of the pleura, and that can happen for a variety of reasons. The simplest to explain is if, let's say we break a rib and we poke a hole in the lung, right? A broken rib is pretty severely broken rib, displaced broken rib, and it pokes a hole in the lung. Well, air is going to leak out of that lung, and it's going to leak into this space. And all of a sudden, you're going to have air in this space instead of, well, in addition to the fluid. Do you still have that surface tension between the visceral and parietal layers? No, right? You lose that connection. You lose this negative intrapleural pressure. This would jump up to zero. This line right here would jump up to zero. You would no longer be attracting the lung to the thoracic wall surface. You no longer have the surface tension, also helping you stick one to the other. And you have what's known as a pneumothorax. Pneumo for air, thorax for thorax, right? Meaning air in the thorax. And because of that, the thoracic volume can be changing dramatically left and right, but because the lung's not stuck to it, the lung is no longer ventilating, right? And you have a collapsed lung, right? So pneumothorax is one version of a collapsed lung. It can be caused by other things like bleeding into that space. It's called a hemothorax. But in the general term, which I believe I gave you last time, is atelectasis. So atelectasis means simply a collapsed lung. Pneumothorax is a specific version of that caused by air in that space. Okay, so there's Boyle's law and ventilation. So what I want to do now is I want to talk a little bit about eupnea and hyperpnea and the muscles that drive these inspiratory and expiratory cycles. Shift gears here. Okay. So let's look at these two terms first off. So we have eupnea. These are kind of weird sounding words. So eupnea, or we can also use similar or synonymous term, would be eupneic breathing. I usually just say eupnea. And hyperpnea, right? Or hyperpneic breathing. Right? So eupnea equals breathing at rest. Right? At rest. That's what most of us are doing as we're sitting here, unless you're panicked about something or you're on a treadmill while you're watching this. Hyperpnea is what's called forced breathing. Right? And these will be terms we'll actually use when we go to a topic about spirometry and the measurement of lung volumes. And we'll have to talk about eupnic and hyperpnic breathing, or eupneic and hyperpneic breathing. And these are driven by the respiratory muscles, whether it's normal breathing or forced breathing, right? They are driven by the respiratory muscles, which we see here. Right? And so if we focus on remember, these are the muscles that will be changing thoracic volume, and because they're changing thoracic volume, they're changing pleural cavity volumes. Because they're changing pleural cavity volumes, they're changing lung volumes. Because they're changing lung volumes, they're changing intrapulmonary pressures relative to atmospheric pressures, and they're generating the gradients required to move air in and out of the lungs. Right? Ooh, sort of a extended sequence of events there, but that's how it works. And so let's focus on our muscles of inspiration and the muscles of expiration here, left and right, in blue and in red. And let's focus on eupnea first, eupneic breathing. This one's really easy. for the principal, when it means sort of focusing on the principal muscles you see listed here, those would be the muscles involved in eupneic inspiration, right? And that's going to involve essentially the external intercostal muscles, the ones between the ribs. They tend to pull the ribs upward. And then the other one is the diaphragm, right? Which you can't really see well here, but it's that dome of muscle kind of right at the bottom of the rib cage, right? We saw it in the previous diagram. And so when the diaphragm contracts, it pulls downward, increasing the thoracic and lung volumes, right? Increasing volumes, decreasing pressures, inspiration. Eupneic expiration, check it out, requires no muscles. It is entirely passive, right? The ribs fall, you get elastic recoil of the lungs, and the diaphragm relaxes, right? And sort of swishes back upward a little bit. Thoracic and lung volumes go down, pressure goes up, and we exhale passively. And eupneic breathing moves probably about half a liter of air with each breath at rest. You'll note now that when we start talking about hyperpneic breathing, or hyperpneic breathing, a couple different ways to say that, we have to add new muscles. We have to add these accessory muscles, right? And you have to add accessory muscles, and this is the reason why. We would have to go back and draw a slightly different graph than the one we had in the previous slide, because the pressures required to move air more dramatically during this forced breathing, right? Instead of a half a liter of air, we need to move 1, 2, 3+ liters of air with each breath. To do that and to move that air quickly, we need to generate larger pressure gradients. To generate larger pressure gradients, we need to change lung and ribcage volume more dramatically, more forcefully, right? We can't sort of use these muscles that just sort of change lung volumes, slightly and weakly. We need to change it much more, I don't want to say violently, but more vigorously, right? And to do that, we need to add more muscles. And so we add in the accessory muscles. And these muscles are going to pull upwards on the ribs, right? They're going to pull upwards on the ribs, usually towards the top of the ribs, right? The sternocleidomastoid pulls upwards on the first couple of ribs, pulls up on the sternum as well. The scalenes similarly pull upward on those upper ribs. Pectoralis minor, a lot of people don't include this as a respiratory muscle. I don't think we need to. It's more of a depress the shoulders muscle. But you get the idea here. If we pull the ribs up more vigorously, then we're going to change our lung volume more quickly. We're going to generate a larger pressure gradient, and more air will move quickly, right? In our hyperpneic inspiration. Now, you'll note in active, and this their term for hyperpneic or forced breathing is active breathing. In active breathing, active exhalation, I should say, we're going to have to add muscles now. And so we're going to pull the ribs downward. We're going to use the internal intercostals to do that. And we're also going to contract all of the layers of the diaphragm, all the layers of the abdominal muscles. Diaphragm is an inspiratory muscle. So what we want to do with the abdominals is sort of compress the belly, sort of pushes your organs upward and shoves that diaphragm upwards to decrease the thoracic volume, increasing its pressure and drive exhalation, right? And so our active breathing muscles are the internal intercostals and all layers of the abdominal muscles. Okay, and once again, just like we had on forced inspiration, by adding these extra muscles, well, by adding muscles, period, right? Because remember, this is passive, right? Passive exhalation. We didn't require muscles, but for active exhalation, we're adding muscles to the action to more dramatically and forcefully change the thoracic volume, to more dramatically and forcefully move air during the expiratory cycle. All right. That is Boyle's Law, ventilation, atelectasis, specifically pneumothorax, and then the muscles of eupneic or normal breathing or restful breathing, and hyperpneic breathing, which is breathing that we do during exercise, known as forced breathing, or you could artificially do it in a, when you hyperventilate.